of the ball boundary that you're on. Okay. All right. So let's talk now about solutions, right? So we've talked about just constructing the Green's function. Let me go more general, right, to solving PDEs with Neumann boundaries. So how to solve the Poisson equation PVP with Neumann boundary conditions, okay? And there's a couple things to keep in mind. So all right, sorry, I know I'm kind of flipping signs around, but you just have a minus sign for the fundamental solution. Okay, so let's consider this boundary value problem. Now we have an inhomogeneous Neumann boundary condition, okay? So, but before we even solve it, right, we make a note that in the case of Neumann boundary conditions, okay, not all BVPs are solvable, okay? So what we need to satisfy is what's called a solvability condition, or in particular, because of its formulation, we call this a compatibility condition, okay? And I'll tell you that compatibility condition straight away. It's that the integral over the volume of your space of F needs to be equal to the integral over the boundary of your boundary condition, okay? So this is your compatibility condition, okay? So how do we obtain this, right? Well, we can work directly from the PD, right? And as you might guess, we're going to, essentially use Green's identity to relate the PDE itself to the boundary condition. Okay. So to show this, right, note the following, that the integral of F over the volume, okay, is going to be equal to minus the integral over the volume of the Laplacian, okay? And then using Green's first identity, okay, we can integrate, we can say that that integral essentially is equal to just the integral over the boundary, or, divergence theorem, multiple ways to get that result. So that's immediately our boundary condition, right? And so we can just write this as the integral over the surface of G in this case, all right? So our compatibility condition, right, comes from analyzing this relationship. The Green's function then is going to satisfy as usual our boundary value problem with homogenized boundaries, okay, and an inhomogeneity that's just a delta source, okay. All right, where as usual y is going to live in U, the open bounded set, okay. Now, in order to satisfy compatibility for the Green's function, okay, we're going to need to modify this, okay? Slightly. And essentially, we're going to make the Green's function the solution to the problem with the delta source plus C in this case, okay? Because otherwise we can't satisfy this this condition, okay? So if we look at this integral, then over the volume, okay, we see that according to our compatibility condition, right, which here, this would be our boundary condition here, this needs to equal just the integral over the boundary of 0, which is going to be 0, okay? So that means that we're left with C, this free constant, is equal to -1 over the volume, the size of our volume, basically the volume of our open bounded set in this case. Okay, so U is the volume of U. Okay. All right. So once we pass that through our solution method, you'll see how it shows up, giving us essentially an additive constant. Okay. So thinking back to the problem that you did before on boundary value problems with Neumann boundary conditions, you know that there should be some free constant here, right? We can actually relate that back to the integral of U, okay? So depending on the particular U that you choose, you'll get an additive constant, which essentially is just the average of that, okay? All right. So if we apply Green's theorem to G and U, okay, then this is similar to the way that we got our solution method in the case of Dirichlet boundary conditions. We're going to take the integral of the product of G with the Laplacian of U minus U times Laplacian of G. Okay. Green's theorem tells us that this is equal to G times the normal derivative of U, U times the normal derivative of G integrated over the surface of the boundary. And we can rearrange this now, okay, and write this as what? Well, we have this essentially is going to be a delta distribution, right? So we could pull it out and shift it to the other side. This is going to be our like the Laplacian of U here, okay, and then we have our just function here G, which is our Green's function, right, is going to give us an integral of G against our inhomogeneity, okay. The boundary terms are going to give us a contribution from this integral over the boundary, right? Which again is going to just involve G. Okay, so I'm just swapping the identities of Y and X in the dummy variables here. And I get an integral of my Green's function against my Neumann boundary condition, okay? And then the last thing I'm gonna get is also a contribution from the Laplacian of G, which was that additive constant now. So I'm gonna divide by the volume of U. And multiply that by just my integral over U in this case. So what is this? Okay, but essentially just the average of U over my domain U. And as we might expect, our solution is unique up to an additive constant, right? Because essentially I can always take U, shift it by some constant, right? And then this will be, the shift that I get will be given by just this integral, right? As long as I'm shifting U by some constant, right? That's just going to change the average of this, right? So this term here represents the presence of that additive constant in my final solution. Okay. Any questions about this? So this is our general solution here. Okay. And the Green's function itself, right, you have to derive differently in the case of Neumann boundary condition. Okay. But the general idea is that you're going to add together these complements outside of the open bounded domain, or yeah, just your domain, right? I guess it's not open in the case of a half space. Okay. So that kind of sums up our discussion of Green's functions. Okay. So as I was saying in the beginning, so what have we talked about? So we've talked about how to what's the idea behind introducing these corrections to the fundamental solution for Green's functions. The idea is usually just to cancel out the boundary conditions. You're always sort of building a function that has homogeneous boundary conditions. In order to derive these formulas for the solutions, in the case of Dirichlet and Neumann boundary conditions, you want to apply Green's theorem, which are sort of like principles for integration by parts in higher dimensions. This is going to involve integrals over the boundary. And when you do that, you end up with these sort of integrals involving the Green's function and the boundary conditions and any inhomogeneities that you might have. Okay. In general, Green's functions, you may not be able to find them so cleanly analytically in this case, but hopefully you got some clue on the homework that another way to find these Green's functions essentially is to use